Hi, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. Today we're going to be talking about Chapter 10 in Organic Chemistry. Organic chemistry is based on compounds that have carbon. That definition has changed over the years. Organic now, we have organic foods and organic growth. And so how this definition has changed over time is something you can talk about in terms of TOK. There are 10 million unique organic molecules, with more being synthesized every day. And one more thing, so it was previously thought that organic molecules can only come from living things, until the chemists, using chemistry, of course, found that they were able to synthesize urea from inorganic reactants, and therefore proving that organic chemistry does not always have to deal with living things. Here is diene. Di talks about two, and ene says double bond, so this is a compound with two double bonds. And a lot of students feel like, after organic chemistry, they are dying. But I promise you, you will be okay. Homologous series have the same general formula, but they differ just slightly, and they show a slight increase in several physical properties, and they have very similar chemical properties. So we see here the difference between methane, ethane, propane, and butane is just adding a CH2 group. Same thing with methanol, ethanol, propanol, and butanol. We're just adding a CH2 group. Now these, since we're adding a CH2 group, there are physical properties that change as we add a CH2 group. One, there's more mass, and since there's more mass, we also have more electrons. And since we have more electrons, we have stronger London dispersion forces. And since we have more intermolecular forces of attraction between these molecules, we're going to increase the boiling point, because it's going to take more energy to break those bonds to turn into the gaseous phase. We also have more viscosity. Think honey has high viscosity. And we're also going to have more density. Notice the increase is also not linear. We have a greater increase at the smaller molecules and less of an increase at the larger molecules. Now, on your right, you see a fractional distillation column. What this does is it takes advantage of the differing boiling points of these compounds. So let's say we had a solution and it had all of these CH4, C2H6, all of these 8 compounds in there, and we wanted to separate them. Well, we could just heat them up and they would separate based on their boiling point, with the lighter gases going all the way to the top and the heavier gases staying at the bottom. And you can see that different members of the homologous series are used in different industrial applications. A couple of things, and there are a lot of things to memorize in this chapter, unfortunately. I'm doing my best to try and help you out with that. But the empirical formula and molecular formula, remember the empirical formula is just the simplest ratio of atoms in a compound, while the molecular formula is the actual ratio of atoms in a compound. Notice that the empirical formula and the molecular formula can be the same, it's just that the empirical formula is the lowest ratio of the compound. We have the full structural formula with all the bonding. The condensed structural formula still kind of shows the bonding because it shows the order in which the compounds are written, and therefore gives kind of clues as to the bonding of its structure. Last thing is the stereochemical formula. You'll learn this more in college, especially in Newman projections and things like that. But pretty much the solid lines represent, these show you the 3D geometrical shape of the compound. And so if we have the solid black lines, that means that it's in the plane of the paper. So it's going to have to practice looking at these three-dimensionally. But the C double bonded C, these are all in one straight plane. If you were to build this in a molecular structure, they would all be in the same plane. However, methanol would have one plane and then one atom coming out towards us. That's represented by the solid dark triangle, and one atom going away from us. That's represented by the kind of dashed triangle there. Remember, you will need to know the functional groups, the names, the IUPAC name, how to name them, and the formulas for these functional groups. Physical characteristics, remember when we're talking about solubility, that water is small and polar, and so it will readily dissolve smaller polar things. So if we look at these two compounds, they are both polar because they have that C-double-O bond, and so there's an uneven sharing of electrons, which leads one side to be slightly positive and one side to be slightly negative. However, the compound on the right has greater mass, so it's bigger, and therefore the one on the left would be more soluble than the one on the right because it is smaller, it is has fewer of those electrons that can dissolve in water more readily. When we're talking about volatility, this is kind of the measure of something to boil or to evaporate. We can see that increasing the strength of the intermolecular forces of attraction will increase the boiling point. And so something like an alkane, which just has carbon-hydrogen bonds, will only have London dispersion forces, while something like a carboxylic acid, it can go through dipole-dipole interactions, which is polarity, and hydrogen bonding, which has nitrogen, oxygen, or fluorine bonded to a hydrogen. And so the greater the intermolecular force of attraction, the greater the boiling point, the less volatile it is. And you can see this whenever if you're trying to fill up your car with gasoline, you accidentally spill some out on the floor and you're hoping nobody saw. That's okay because a lot of those are just alkanes, and so they have weak intermolecular force of attraction, and so they will evaporate into the air. Primary, secondary, and tertiary compounds, to do this, you just count the number of carbons the carbon that you're looking at, or the atom that you're looking at, is bonded to. If it's bonded to 1 carbon, it's primary. If it's bonded to 2 carbons, it's secondary. If it's bonded to 3 carbons, it is tertiary. Now what's the point? Why do we do this? Well, imagine this tertiary carbon trying to get into a really tight space in a compound. It's going to have a hard time doing that because it has so many groups around it. Whereas a primary carbon might be able to get in there and bond with a certain compound if it was really crowded. And that's why we look at that. One last little tip. If you are looking at a compound like this, is this a primary, secondary, or tertiary carbon? You might be inclined to say that it is a 0 tertiary carbon, or a 0 prime carbon, because it's not bonded to any other carbons. That would be incorrect. This is actually a primary carbon. So if it's not bonded to any other carbons, it's still a primary. And we'll stop there for today.